So as Melissa said, I'm a researcher at the Climate Change Research Center in Sydney. And I actually been working with a natural variability associated with El Niño Southern Oscillation and the impacts of El Niño on Australian rainfall. But today I'll be talking about climate change. I'll give a general overview of climate change because I think some of you might be from different areas, so I think it's nice to cover, try to cover a lot of things in 1 hour. Okay, so what I'll show in this lecture, I'll give a brief overview of climate, past climate variations, and I'll talk about global warming, show some IPCC emission scenarios, and I'll show then climate projections and changes in tropical circulation as the Hadley cell, and in the Walker circulation with projections in the El Niño Southern Oscillation. This slides is on the web, so you have all the material, and I also have a Word document with lots of the references that I'm showing here, but most of the material is based on the IPCC. So I'll start talking about the greenhouse effect. I know everyone knows what a greenhouse effect is, but I just want to remind that it's a natural phenomenon occurring on Earth. And basically, the atmosphere is transparent to solar radiation, but it absorbs the infrared radiation that is emitted from the planet. The majority of the gases in the atmosphere are actually not good greenhouse gases. It's only a tiny amount, less than 0.1%, that is actually greenhouse gases. But it's responsible for keeping the planet warm. And if we didn't have this atmosphere, the planet would be cold minus 15 degrees or 18 degrees Celsius. Okay, but the temperature in the planet has varied a lot since its beginning, since its evolution. We show here the temperature varying from the Phanerozoic to the present, and you can see a huge variation in the temperature, especially in the earliest period where the continents were rearranged and released a lot of CO2 in the atmosphere, so a lot of tectonic movement there controlling these variations in temperature. And then the temperature went down to this period in the Pleistocene, where you see a lot of up and downs in the ice age, and then it went up to a more steady state in the Holocene and the present that we are here. So if we look at the ice age, if we look at the past 400,000 years ago, we see this graph. It's an ice core from the Antarctica, and very famous. Everyone probably have seen that before. The red line is the variation in CO2, and the blue line is variations in the temperature. And you can see that they are highly correlated. One goes up and the other one responds to it. And in this time series, you can see that these fluctuations in temperature and CO2 are basically dominated by what we call as Milankovitch Cycles, Milankovitch theory. So Milankovitch was a Serbian astronomer who postulated that small variations in the orbit and the Earth tilt would be very important for the amount of solar energy reaching the planet. And basically, there is this three mechanisms: the eccentricity of the orbit, the obliquity, and precession, with very well-defined periodicity. And when they put them together, is Milankovitch theory, it explains a lot of the past variations in the temperature of the planet. So it explains this interglacial cycles, as you can see in the Vostok ice core here in blue at the bottom, and also it selected records from China. Okay. But if we look back at variations in temperature and compare now with the present climate, what do you see? Let's focus in the bottom panel, in the top panel. So we have the cycles here again. Now it's 800,000 years ago. So we see these variations in temperature now in green, and variations in CO2 here down. If we focus in the more recent period, the last 2,000 years, you see that the temperature has been more or less in equilibrium. And then, since the Industrial Revolution or 1850s, more or less, we see this huge increase in temperature and in the CO2. Note that the scales here are different. I don't know if it's very hard to see, but they are different in those graphs. But just to focus in the more recent period, you can see this increase together with the temperature. Okay, so it was about, I would say, mid-20th century, like 1950s. People believed that all the CO2 that we put in the atmosphere would be observed by natural reservoirs, the natural sinks in the oceans and land. And was about 1958 that Keeling started to measure CO2 in the atmosphere. Oh, let's put a measurement in. Let's do the measurement. He put started to measure in Hawaii, Mauna Loa Observatory, and he noticed that the CO2 increased. Not him, but we can see that this is the first proof that the CO2 actually has been accumulating in the atmosphere. So it's not all the CO2 that we put in the atmosphere that has been equilibrated and observed by the oceans and lands. And he also noticed that there is this variation in like the annual cycle in CO2 with the absorption of CO2 when the plants in spring grows and then dies in winter time. So that's it became very famous, the Keeling Curve. There is a website with all the history of this Keeling Curve, how it started, the impacts, and lots of pictures and movies that I have in this Word document that I'll send later. And so if we focus in the CO2 concentrations in the past 400,000 years, we see a variation from about 180 parts per million to 300 ppm. The current level nowadays surpasses the 400 ppm. And that was the latest CO2 in May this year in this observatory. Okay. We also have detailed measurements of how much oil and natural gas and coal we burn every year. And from that, we can estimate that about 0.5% of this cumulative anthropogenic CO2 emissions between 1750 to 2011 occurred in the 40 years. And about 40, sometimes we say like 45–50% of these anthropogenic CO2 emissions have remained in the atmosphere since then. And the rest has been stored in reservoirs. But it's not only CO2 that has been increasing. We see, when I say increasing, it's CO2 concentrations in the atmosphere. But we also see an increase in concentrations in methane and nitrous oxide. So basically, methane has increased 150% since 1750s, and 20% an increase of nitrous oxide since then. Is a huge increase. So together with this increase in concentrations of greenhouse gases, we also observe the rise of the temperature in the planet. And the top left panel shows the global land and ocean surface temperature anomaly from 1850s to 2012. You see, this is a consistent record across different data sets and has been increasing dramatically since, especially in the past 50, 60 years. The linear trend over that period is 0.85 degrees Celsius. And on the right-hand panel, you see that this warming at the surface occurs in different data sets, regardless the techniques for interpolation or treatment of this data that we have, and also in different periods. Okay, but it's the greenhouse gases the cause of the recent warming. And one of the things scientists try to do is to use climate models, try to reconstruct this observed temperature that we see, this time series that is in black here. And they use a lot of, the temperature, you see a lot of natural variations, interannual variations in this time series. Those fluctuations from the El Niño Southern Oscillation on more decadal timescales. You see those related to AMO, Pacific Oscillation, decadal oscillation as well. But we can only explain this warming, especially from 1950s, when we consider all the natural and anthropogenic variations. I'll show that there is this link. I think some of you have seen that. I'll just try to see if I can play. If not, we come back at the end. Yeah, I don't think it's going to work. Oh. Okay, I'll try to come back at the end, but it's a nice reconstruction using climate models where they put like the orbital changes and they sum up what is due to anthropogenic causes, land use, ozone, and aerosols all together. And they can only explain this black curve once we sum the anthropogenic and natural forcings. So the IPCC states that it's extremely likely that human influence was the dominant cause of global warming since 1951. When they say extremely likely, it's more than a 95% confidence on that. And how do you know that the world has warmed? Well, I've shown before that the surface air temperature is the best indicator that this has happened. But scientists actually use a lot of other evidence and multiple indicators to reach that conclusion. So together with change and increase in the temperature at the surface, we also see a consistent change in temperature across the tropopause, the troposphere, deep in the oceans. We see snow cover, glacier volume reducing, a sea level rise, and changes in water vapor. I'll show some of those trends, the observed trends we have in the past 50 or 100 years. So those figures are from the IPCC. You can also have this and check all those references. So consistent with a warming at the surface, we see this warming at the lower troposphere. So temperature has been warming here in the lower troposphere, and we see a decrease in the lower stratosphere. which is also shown not only in the satellite data, but with radio sound data sets. In the tropics, this cooling in the stratosphere is actually less consistent across different data sets. It gets better when we use the satellite area, but there is a huge uncertainty in the, not in the sign of this trend, but in the amplitude of this trend. Sea ice changes as well. There is a dramatic decline over the past 20, 30 years in the Arctic, but I won't talk about sea ice, especially because I'm Brazilian. I can't pronounce certain words correctly, so the double E generally comes as a strange word for me. I try to avoid to work with the high latitudes. And also we are in a tropical meteorology course, right? But the oceans, the ocean might be probably the most important component on the climate system to capture this global warming. Because of the high heat capacity of the water, it just tends to kind of delay and keep the imprint of the global warming in the oceans there. 90% of the energy accumulated from 1971 to 2010 has been stored in the oceans, and only about 1% in the atmosphere. And the top layer of the ocean, the upper 75 meters, accumulated the most of this energy and has warmed about 0.11 degrees Celsius from 1971. And this has consequences for other variables too in the ocean. So we see the surface temperature has been warming again, now different, five different data sets here in agreement. And we see that the sea level rose from 1900 to 2010 by about 20 centimeters. Ocean heat content is also has been increasing. So a lot of those changes occurring in the ocean, and this is especially sea level rise. We have a high confidence in these measurements in the past 30 years, 1970s at least. How precipitation changes? So the trends in precipitation is actually, we have low confidence in the trends in precipitation. And that's because, as you see here, the data sets maybe is easier to see. The global trend in precipitation actually doesn't even agree on sign, and there is a huge uncertainty in these trends, especially in the tropics. So we can't say much about global precipitation, how it has changed since 1950s. The most what we can say is that the mid-latitudes in the northern hemisphere has been slightly wetter than before. But what we can say with high confidence is the trends in extremes. So especially extreme temperature has been, we have more warm days and warm nights, and the trends on cold nights and cold days are negative. And this is nicely shown as well with the shift in PDF. So comparing the first half of the 20th century with the latest one, we see a shift towards the right in this PDF that just increases the frequency of those extreme events. So less cold nights and days and more warm nights and days. Okay, but so I've shown how the trends have been the past 50 or 100 years, and I've also showed to you that we've been putting more CO2 in the atmosphere, and this has been accumulating there. And once we cause this perturbation in the climate system, we introduce a radiative forcing. Basically, we're putting more CO2 in the atmosphere. We are introducing a forcing there, and the climate system needs to come to an equilibrium after this imbalance this radiative forcing can be, we can talk about radiative forcing in several ways. It can be caused by an increased solar activity. It can be caused by volcanoes. It can be caused by a lot of factors. But here we are more interested in the radiative forcing that comes from the increase in greenhouse gas concentration. So it's estimated that about half of the observed surface warming from 1951 to 2010 was caused by an increase, anthropogenic increase in greenhouse gas concentrations. And this radiative forcing from 1750 to 2011 is estimated at 2.3 watts per square meter and has increased more in the past 3 years, so since the 1950s, 1970 actually. The CO2 is the major contributor to this radiative forcing, so we can see here that CO2 is the biggest one. And these three gases, the CO2, methane, and nitrous oxide, they account for about 80% of the total anthropogenic radiative forcing in 2011 relative to a pre-industrial period. So once we perturb the climate system, the planet starts, it can go either way, so it triggers feedbacks. It can amplify this initial perturbation by having positive feedbacks, or it can dampen this initial perturbation by a negative feedbacks. And feedbacks is actually something that is not very uncertain, but there are a lot of things that we still don't know. One of the things that we use, what we want to know actually is we know how much CO2 and the forcing that has been caused in the atmosphere. We want to know how much warmer will be the global climate after putting this radiative forcing, after reaching an equilibrium. And for that, we use the climate sensitivity parameter. So it just tells us how much warmer will be the climate once we have a double CO2 concentration. So sometimes scientists look and compare models. Your model, what is the climate sensitivity in your model? This is what they use, the climate sensitivity parameter. And it's actually can vary a lot from model to model, and we can't measure that directly. So we have to estimate by several ways. But basically, either they use conditions in the past when we had a more stable climate, and they estimate the climate sensitivity, or they use a range of models to estimate that as well. Paleoclimate records, and the IPCC reaches a conclusion that the equilibrium climate sensitivity is estimated to be between 1.5 degrees and 4.5 degrees to 4.5 degrees. This is a huge range. The mean is 3.2 degrees Celsius. Okay, and what complicates this climate sensitivity is actually the feedbacks that we have in the planet. The most important ones, we have a lot of feedbacks, but the most important ones, once we increase the greenhouse gas concentrations, is the water vapor. So the warmer the atmosphere can host more moisture, it warms more, and enters in a positive feedback. The clouds feedback, which is a bit of black box and in the models, and it's probably one of the biggest uncertainties. And the ice albedo feedback, that with warming melts glaciers and sea ice, lower sea ice, and then enters again in a positive feedback. And these three main feedbacks increase the climate sensitivity to about 2 to 5 degrees Celsius. Okay. But one thing that is useful, I guess, for everyone is to know, once we have this perturbation, we know the radiative forcing in the atmosphere, we know how much we warm, what will going to happen with the future? What are the projections? And basically, we need that because we need to come up with a plan for adaptation and mitigation of the negative effects or positive effects of global warming. There is this series of climate models or climate simulations where they use those emission scenarios. In the past, they used a lot of, they tend to use the concentration scenarios where they prescribed the concentrations of greenhouse gases in the atmosphere. And in the last IPCC, they basically used the emission scenarios. So they come up with these 4 scenarios, and it basically is based on the population growth, the renewable energy that we will have in the future, innovations, technological innovations, and economical growth. So these 4 scenarios, which I'll say are RCP, the largest one is the RCP 8.5, that reaches about 8.5 radiative forcing by the 2100, where you can see here in red. And the lowest one is the RCP 2.6. This is the atmospheric CO2 associated with those 4 scenarios. And we see that the air temperature changes with about 3 degrees by the end. This is at 2100. So the strongest scenario will have like 3 degrees Celsius warming by then. What is interesting is after 2100, they decrease those emissions. They put to 0, but the ocean thermal expansion is still going after that, even with the equilibrium of the air temperature. So the air temperature reaches an equilibrium, but the oceans still keep warming. Okay, I'll show quickly a few of the projections for the strongest emission scenario, the RCP 8.5. So here, actually, this is showing the strength of the emission scenario. So the lowest one to the highest, as you can see, it warms everywhere, especially over land. So land tends to warm faster. We also see an increase in the temperature, in daily temperature, extreme events, especially the coldest temperature being warmer in the future. And rainfall is a bit different. There isn't this uniform changing rainfall. But what we see is an increase over the tropics in the equatorial Pacific. This varies according to the seasons. But the pattern that we can say here is that it will tend to increase the precipitation where we have, in the tropics, where we have largest precipitation, and in the mid-latitudes as well. And it tends to decrease where precipitation is lower. And because of that, this pattern is commonly referred to the wet gets wetter and dry gets drier. There is a lot of debate in the literature about this topic, especially because this projections in rainfall doesn't have the same confidence as projections in the temperature. And a lot of the mechanisms are still being studied and are not definitely science in that topic is still going on. But what we see is that it works quite well over the ocean areas. Over land, the story is a bit different. It depends a lot on vegetation and how those are represented in models, which varies a lot, and there is a lot of uncertainty in models. So this wet gets wetter dry that gets drier, it doesn't work completely like over the globe. It works well for the areas over the ocean. So, okay. So how the circulation in the tropics will change? Here I'm showing the temperature. That's the height in the atmosphere. That's the latitude. What we see is a warming in the tropical upper troposphere and a cooling in the stratosphere. This is for RCP 8.5. This projection is not so strong for the lowest emission scenarios because this is an effect, it's a combined effect of the greenhouse gases and the aerosols. And in the lower scenario, emission scenarios, the aerosols basically counteract the recovery of ozone, actually, counteracts the increase in concentrations in greenhouse gases. So it's, we have actually not, like it's a medium to low confidence on this, this change. The zonal wind, this is the zonal mean wind. That's the black lines are the control run, the pre-industrial run, the mean, and the shading is the change. So you can see that there is an intensification of the zonal winds, especially here in this part in the stratosphere, and a poleward shift and intensification of the, especially in the southern hemisphere tropospheric jet. And associated with that, also we see this pattern in sea level pressure, which shows a strengthening and a poleward shift of the surface westerlies. All those changes are consistent with the Hadley cell expansion. So there is this paper by Liu and collaborators in 2007 where they show this widening of the Hadley cell. So basically the tropical regions becomes broader, and there is this poleward displacement of the subtropical dry zones. What he shows here is the displacement of the Hadley cell boundary. So the northern Hadley cell boundary becomes shifting northward, and southward the south part of the boundaries, and the displacement of the dry zones. This projected widening of the tropics is, I would like to make clear that be careful with that. The projections have a medium confidence, medium to low confidence on that. There is a lot of observed changes towards shifts of the westerlies in the southern hemisphere especially that have been associated with the ozone depletion. But, and there's widening, and there is a lot of debate in the literature. You see a lot of the references that I have in the Word document for you if you want to go into details of that. But basically what this Liu and collaborator paper in 2007, what they found is that there is an increase in the static stability in the subtropical regions that basically pushes the first zonal baroclinicity, where we have the eddy-driven jet poleward. This is one of the theories. There are other papers also talking and linking that with changes in the sea surface, even the sea surface temperature gradient with this poleward shift as well. So how one of the things that we have with more confidence, we know with more confidence, is the changes on the Walker circulation, more than the Hadley circulation. Actually, the changes in the El Niño, how El Niño southern oscillation will change in the future. Well, the Walker cell tends to weaken, and this has been a robust change since the previous IPCC report, we see that the Walker cell weakens by the late of 21st century. We have a weakening of the easterly winds in the equatorial Pacific. We see so here I have the climate change scenario. So we see a weakening of this easterlies. We also see the ocean temperature warming faster in the equator than off equator. We see that the thermocline is expected to flatten and to show an increased mean rainfall over the eastern Pacific and along equatorial Pacific, actually, as I've shown in the slides before with rainfall projections. And despite all these changes in the mean circulation in the Walker cell, a paper in 2010, 6 years ago, in Nature Geoscience, came to the conclusion that it's not yet possible to say whether the El Niño Southern Oscillation activity will be enhanced or damped, or the frequency of those events will change. Some of the models show this increase in the variability of El Niños, others show this decrease, and there was no consensus on that topic. So it was about last year, 2013, I think, that one of the colleagues, Agus Santoso, with Shane McGregor, who was a lecturer here, he's a lecturer in this winter school, and other colleagues as well, that published this paper in Nature showing, instead of looking at the sea surface temperature for El Niño Southern Oscillation variability, they look at the currents, they look at the ocean, other metrics. And they were trying to explain those events, like the events in 1982 and 1997, who had this currents, these eastward propagating, what they call eastward propagating El Niño. So basically, there was a reverse of the ocean currents in this extreme El Niños, the super El Niños. And what they looked at in the future, and they saw that the number of events that we have eastward propagating El Niños will increase a lot in the 21st century compared to the 20th century. So as the first paper to show, look, we don't see any robust changes in El Niño in general, but if we look at extreme El Niños, then we see a change in these extreme El Niños. They will become more frequent in the future. So another Nature climate change paper in 2014 from colleagues looked at another variable. So again, Agus looked at the ocean. He looked at the equatorial rainfall. So El Niño has this strong coupling in the atmosphere, and there's a strong response in rainfall in the Pacific. Basically, extreme El Niños can be also classified by this rainfall, and this is observations, sea surface temperature, and the green line indicates the 5 millimeter per day rainfall. So you see that in a moderate El Niño, you see that the sea surface temperature extends to the Central Pacific, but not to the Niño 3 region. And rainfall is the same thing. It only extends to the Niño 3 region when we have the super El Niño, this El Niños as in 97 and 82. So they use that as a metric, the 5 millimeter per day rainfall. And this is because also it shifts the intertropical conversion zone in the eastern side of the Pacific towards the equator in extreme El Niños. And the models could capture that quite well, actually, compared to observations. So then they say, look, the mean state has been warming, and it warms more in the equator than off equator. This decreases the gradient in the SSTs, right? Makes it weaker, those zonal SST gradients. And they look at the frequency again of those extreme El Niño events, And what they see is because you see a faster equatorial Pacific warming and with the weakening of the Walker circulation, it makes easier to shift the convection and rainfall from the West Pacific to Central Pacific, and the ITCZ to put ITCZ back to the equator in the Niños 3 region. And they concluded that there is almost a double of the events in the future. So again, showing an increase in extreme El Niño events in the future. But they wanted to see about El Niños as well, so not happy with his previous paper of El Niños. They also looked at extreme La Niña events. And La Niña events also tend to increase in the future. This is because over land we see a stronger warming than over the oceans. So there is a faster warming over Indonesia, and also in the projections we see a warming, more warming at the surface than at depth, so it increases the vertical gradient and the temperature. And because La Niñas tends to be followed by extreme El Niños, like 97, we also see an increase of extreme La Niña events. So they summarized everything in a review article in Nature again, and they look at El Niños events that actually were preceded by positive IOD events, and then followed by La Niña events. So the whole story here. So positive IOD El Niños peaking during springtime, then El Niños in Austral summer, and then following the next year by La Niña events. And they found that the frequency of those extreme events will increase one event per 180 years approximately to one event in 48 years. Yeah, okay, I'll stop now, and I'll try to go back to two of the things that I wanted to show that I couldn't do. Let's see if I can find what was here. So one of the things was the reconstruction of this warming. Oh, no. Let me see. I'll just copy and paste. I find this really cool. I wanted to share that. You've probably seen that, but yeah. So this is a simulation. It's asking what's really warming the world. And it has this observed temperature, global temperature anomaly, and the observed is there. And then they put all the forcings together. So it starts with the orbital changes. Is the orbital changes explaining that? Well, it might explain something in the beginning of this time series, but not quite. And then the solar forcing, put together the volcanoes, and this is a very important part of our variability, because it has this huge cooling when we have those volcanic eruptions. But it can't explain, of course, the warming in the past 50 years, and then put them all together. And yeah, maybe explains part of this time series in the beginning of the time series, but then the natural factors won't account for the observed warming since 1950s. Then it includes land use. There is a slightly cooling effect here. Ozone. The aerosol pollution, this is one of the biggest uncertainties in the models as well. And there is this cooling there. And then comes greenhouse gases. So you see this huge warming. And put them all together, you see that then starts to come with the human factors can reproduce the time series. So comparing, put them all the factors together, the natural factors, human factors, then we come up with a more fair comparison with observations. The other one that I want to show, I'll say there is a movie, and didn't work as well. Let's see if I find here. Is how the CO2 is 1 year. I don't know if you're seeing that. Is 1 year of CO2 in the planet. It's a very nice simulation.
Hi, this is Bill Putman. I'm a climate scientist at NASA's Goddard Space Flight Center. What you're looking at is a supercomputer model of carbon dioxide levels in the Earth's atmosphere. The visualization compresses 1 year of data into a few minutes. Carbon dioxide is the most important greenhouse gas affected by human activity. About half of the carbon dioxide emitted from fossil fuel combustion remains in the atmosphere, while the other half is absorbed by natural land and ocean reservoirs. In the northern hemisphere, we see the highest concentrations are focused around major emission sources over North America, Europe, and Asia. Notice how the gas doesn't stay in one place. The dispersion of carbon dioxide is controlled by the large-scale weather patterns within the global circulation. During spring and summer in the northern hemisphere, plants absorb a substantial amount of carbon dioxide through photosynthesis, thus removing some of the gas from the atmosphere. We see this change in the model as the red and purple colors start to fade. Meanwhile, in the southern hemisphere, we see the release of another pollutant, carbon monoxide. This is a gas that's both harmful to the environment and to humans. During the summer months, plumes of carbon monoxide stream from fires in Africa, South America, and Australia, contributing to high concentrations in the atmosphere. Notice how these emissions are also transported by winds to other parts of the world. As summer transitions to fall and plant photosynthesis decreases, carbon dioxide begins to accumulate in the atmosphere. Although this change is expected, we're seeing higher concentrations of carbon dioxide accumulate in the atmosphere each year. This is contributing to the long-term trend of rising global temperatures. The Orbiting Carbon Observatory 2, or OCO2, will be the first NASA satellite mission to provide a global view of carbon dioxide. OCO2 observations and atmospheric models like GEOS-5 will work closely together to better understand both human emissions and natural fluxes of carbon dioxide. This will help guide climate models toward more reliable predictions of future conditions across the globe.
Okay. This was supposed to go with the Keeling Curve, showing 1 year of CO2 in this seasonal cycle. Well, I think I'll stop here now and I'll take questions. Thank you. Yeah, those papers that I've shown in the last few slides just came out in 2014 and 2015. So it's actually, after the IPCC. So the changes in the Walker circulation has more confidence than the changes in the Hadley still. But changes in the frequency, intensity of El Niños, frequency of El Niños and La Niñas is just coming up, like in the past year or so.
So the confidence hasn't been really quantified, like?
Yeah, those ones that I showed to you are based on 19 models. So it's not the full range of the CMIP5 models that are available, but only those that can reproduce an extreme El Niños. And they don't see any significant change in El Niños or La Niñas, moderate El Niños or La Niñas, so weak events. Are only those that are extreme El Niños, those that are characterized by a lot of rainfall, high rainfall in the Niño 3 region, and the reverse of the currents in the ocean. You're welcome. I guess everyone is tired with the last lecture of the week. Is there anyone doing any projects on ENSO here, or climate change projections? So maybe I'll come and talk to you after that.
Yeah, that will be around for a little while.
Maybe 1 hour. Yeah. Thank you.